Okay, so hopefully you have taken some time to look at the log function, how logs work. You have proven some of the properties of logarithms, which are super important. Those proofs exist in most Algebra 2 materials, so I'm not going to retread that here. I do want to take a look in our time at the real exponential function. And I want to play with a couple of its properties that matter for us as secondary educators. So first things first is the following lemma. If alpha is, oh golly, if alpha is greater than 1, then the limit of alpha to the 1 over n as n goes to infinity in the integers is 1. First, we establish the result for the integers. As n goes to infinity for integer values of n, that limit is 1. How do we know? Well, because alpha is greater than 1, and because algebra tells us that alpha to the n minus 1 over alpha minus 1 is alpha to the n minus 1 plus alpha to the n minus 2 plus 3 dots plus alpha plus 1. This is just algebra. It follows that, well, alpha to the n minus 1 over alpha minus 1 is greater than or equal to, well, let's consider. This alpha is greater than 1. We raise it to a power that's greater than 1. And this is an alpha that's greater than 1, and we raise it to an integer power that's greater than 1. In fact, all of these end up greater than 1, greater than or equal to 1. How many are there? There are n. So alpha to the n minus 1 is greater than or equal to n times alpha minus 1. Now, it is also true that alpha to the 1 over n is greater than 1, because alpha is greater than 1. Just reminding, if alpha is greater than 1, and we take a root of alpha, any root of alpha, that root must be greater than 1. So alpha to the 1 over n must be greater than 1. So it must be that if we replace alpha with alpha to the 1 over n, this must be true. And then we can do some algebra. This is alpha. I mean, nothing terribly complicated here. Let's see, a little bit of distribution. You say you want a distribution. Well, you know. And so it follows that alpha to the 1 over n is less than or equal to, kick this over and divide, a plus n, I'm sorry, alpha plus n minus 1 over n. It also must be true that alpha to the 1 over n is greater than 1. That's got to be true. And so this alpha to the 1 over n is trapped between two quantities. As n goes to infinity, that goes to 1. As n goes to infinity, Well, what happens to this? Alpha is a fixed number, so n goes to infinity. That's a fixed number. That's a fixed number. That's n. That's n. That goes to 1. So, by the squeeze theorem, the limit as n goes to infinity of alpha to the 1 over n is 1. Now, here's why that's a big deal. It follows immediately that the limit of alpha to the r as r goes to 0 if r is rational is 1. N goes to infinity, that goes to 0, and it doesn't really matter what the powers are. If this is going to 0 and it's rational, that limit is 1. And that's a sort of key result. The big result, the proof of it's in your text, so I don't have to go too crazy with this, but I can cite the result. We let gamma be a real number, and we let the sequences r sub n and s sub n be sequences of rational numbers converging to gamma. Then both sequences converge to the same. I am so wrong. I don't care about r sub n and s sub n. Gamma to the r sub n and gamma to the s sub n converge to the same real number. The proof of that is in your text, and it's worth a read. It's a great proof for my friends who are taking Math 324 real analysis. It's going to be a little bit over the heads of people who have not taken real analysis. Why do we care about this? We care about this because we want to show that alpha to the x, the exponential function, is well defined. We want to establish that we're only getting one output for every input. And we want to show that the function basically behaves well. So in the same way that we said early in our course that if you take any Cauchy sequence that converges to a particular real number, any Cauchy sequence will do. That's what this is saying. It doesn't matter what sequence r sub n or s sub n you choose. If that sequence is a sequence of rational numbers that converges to gamma, then we can use that. We can use those sequences interchangeably. Because we can use those sequences interchangeably, in the proofs that follow, we'll pick our sequences carefully to have the properties we want them to have so we can do the things we want to do. Okay? Take a breather, get a quick drink, come on back. We'll talk about why the exponential function is continuous.